The next part of waves that we can look at are the wave properties themselves. So, to review, we have a medium, which is a continuation or a continuous collection of particles. Again, a medium is just the type of material or the substance of which the wave is traveling through. A pulse is a single disturbance in a medium that transmits energy without transmitting mass. Always, always, always energy without mass. Always. A wave itself is a regularly repeating pulse. So when we're talking about a wave is made up of multiple pulses together. So we have two different types of waves that we're going to talk about. The first is called a transverse wave. And when you have a transverse wave, the direction of your wave's travel is perpendicular to the motion of the medium. So it's perpendicular to the motion of the medium. So what does that mean? That means that if my medium is traveling to the right, my wave particles will be vibrating up and down such that it creates a perpendicular angle or 90-degree angle. This would be an example, would be something like on strings, like strings on a guitar, or on any kind of instrument. I actually included a video, which is a really, really cool video that they take an iPhone and they put it inside of a guitar and you see the different waves, and depending on the pitch of each sound wave, how tightly those strings are wound, you see the difference in the waves. It's really, really cool video, and I put it on Google Classroom for you. So when we talk about these waves, we're talking about different things that are acting here. So first, the distance from one crest to another is something that is called wavelength. So the length of your wave. This is this variable right here. It looks like an upside down Y, but it is the Greek letter lambda, and it looks just like this. The maximum height of a wave above your equilibrium, we talked about last time, is something that's called amplitude, and that is the letter A. So now, when we look at this wave here on the left, this is a wave. So it starts right over here at the beginning. It travels through one pulse, one other pulse, back up, back down. So there are multiple wavelengths that are in this particular picture here. So when we're talking about a wavelength, okay, there we go. When we're talking about a wavelength, you can see one wavelength represented in two different ways. So you can either see one wave look like this, where this is your equilibrium, or you can see one wave look like this, where that's your equilibrium. If you were to take, if you were to take this piece right here and this piece right here and combine them, you're going to end up with the same picture. So it doesn't make a difference which way the wave is drawn. The wave, you do have to be familiar with both. So the wave can either be represented by the first or second picture. Regardless, both pictures represent one wavelength. So now, when we look back here at this diagram here, this picture, they're showing you that your wave, the speed is traveling to the right. They're telling us that between this crest and this crest, where the top of your wave pulse in the positive direction is called a crest. The bottom in the negative direction is called a trough. So in this picture here, you have going from one crest to the next crest, one wavelength. They're showing you again that you're traveling to the right, which means that your particles are going to be moving perpendicularly. That's just a straight definition. Waves itself, this particular unit, there's a lot of definitions and a lot of review that you need to make sure you dedicate time to. The definitions themselves are not difficult. It's just you need to make sure you can differentiate between them all. And the last thing that it shows us here is the amplitude. That's this A over here. And amplitude, again, goes from your equilibrium position to the height of one pulse. So whatever that value would be in meters, that would be our amplitude. A longitudinal wave looks something like this. So it looks definitely different. If you look at both pictures, one is perfect, perpendicularly oh my gosh, it says a tongue twister there, are perfectly straight lines. And one looks like a curved wave, like what you would probably draw if you wanted to draw waves on a picture or something. So when you're talking about a longitudinal wave, here, the direction of your wave travel is parallel to the motion of the medium, meaning that your wave, if your wave is traveling to the right, then the motion of your particles are going to vibrate horizontally. An example of this, the only type of longitudinal waves that we are going to discuss are sound waves. That's it. Every other wave that we talk about in this class will all be transverse waves, all of them. So the only one that you need to be familiar with longitudinal is sound. Longitudinal waves can, or I should say sound waves, can also be called mechanical waves, which you'll see them written as sometimes as well. So you do have to make sure you are familiar with the other term that they could use. So the distance from one compression to another, again, is your wavelength, the Greek letter lambda. The intensity of a compression, intensity, how intense you are doing something, is the energy, and that is, again, your amplitude. So when you look at this wave here, they show you that your wave is traveling to the right. It won't always be. It could be traveling to the left. Just depends on what the problem tells you. So again, you see that your motion is going horizontally. So again, I encourage you to check out that video of the difference between the transverse and longitudinal waves. That's not something I can like physically show you through this static picture here. So make sure you go and look so that you can see the exact direction that you have in these particles. On here, in a longitudinal wave, if you notice, you have the lines, they're not just drawn like randomly. It's not drawn just to look like a barcode or anything like that. You have some lines. Let's get a different color so you can see what's happening here. You have some lines that are pushed together. So all of these ones in the green here. And then you have some that are spread out, like all the blue ones. So you can see there's a difference here in the way that the lines are drawn. So when you're talking about longitudinal waves, wherever you have the lines that are close together, that's what we call a compression. Wherever they are spread apart, this is called a rarefaction. So now we're able to do some solving of some missing things that we have. And so when we talk about waves, waves have a direction of travel, then they have a velocity. So if they're moving, they have a velocity, which can be calculated by looking at distance and time. So, okay, so we know already the very first equation that we ever learned is V equals D over T. We did that. We said, okay, well, your velocity is equal to your displacement over your time. Well, that's great, but we can't necessarily say that for a wave because we're dealing with different variables. So when we talk about distance, again, we are talking about wavelength, and that's our lambda. When we talk about time, so when we're talking about time in terms of waves, this is something that's called the period, and that is capital T. So period, when we're talking about waves, period is the number of seconds per one cycle or per one oscillation. So if you're able to travel around a track, running the track, say in 7 minutes, well, then your period is 7 minutes. So the time that it takes to go around one time. So now when we talk about that for our waves here, we can replace these variables into our old formula. So instead of distance, we have wavelength. Instead of time, we have period. If you look on page 5 in your reference table, that's where waves are, waves and oscillations. So we are going to be looking at the first two formulas right now. And if you look at that, the formulas on that page, you will see a formula that looks like this, where it says T is equal to 1 over F. T is your period, what we already talked about, and F is something that we call frequency. So frequency, F, is the number of cycles per 1 second. So you should see when you're looking at both of these definitions here, period and frequency, you should see that they are the opposite, right? Which is why in the formula you have the 1 over F because they're inverses of each other. So now we can go through and we can add this formula into the one that we already came up with here. So we have wavelength over, and I'm just going to replace my T with what it equals, 1 over F, where this is like a fraction and a fraction. We don't want it, we want to simplify as best as we can. And you should know, I think they call it like keep change flip or something like that in math, where you want to multiply by the reciprocal so that we can get rid of the bottom. And you end up with V equals frequency times wavelength, which if you look on page 5 in your reference table, that is the other equation that I said we were going to use, the first two formulas. So you have the velocity formula here for waves. You also have the period formula for waves. Those are the first two formulas. Okay. So now, as waves travel, they lose energy. They lose energy which is associated with amplitude, as we already know, but not speed, frequency, or wavelength. The speed of a wave depends only on the medium through which it travels. When a wave changes mediums, it is both transmitted partly and partly reflected. That's what we talked about last time. Transverse waves, again, I encourage you to look at the videos on these here so you could see the difference. Transverse waves move faster in sparse or low dense materials, and longitudinal waves move faster in dense materials, which is why, like sometimes if you want to like spy on somebody in the room next to you or something like that, you're able to put your ear against the door, or and you'll be able to hear it better. Or if you have, say, like an earthquake with like aftershocks, if you put your ear on the ground, you're able to hear what's going on as the waves traveling towards you. Or like, for instance, if you have people like walking around you, if you put your ear on the floor, you should be able to hear the impact of those waves as it's traveling. So sound travels faster in dense materials. All of the other waves that we talked about will travel better in less dense materials. The last thing that we need to discuss before we do some problems here is what it means to be in phase. So if you are in phase, 2 points in a wave must be traveling in the same direction and have the same displacement from your equilibrium. So what that means is if I have a wave, okay, and I have all these different points on my wave, I will tell you that my wave is traveling to the right. So my velocity is traveling to the right. And I say, okay, well, I want to know about this point right here. What point is in phase? Well, it means it has to be traveling in the same direction. So obviously you want, if something is going to be in phase, then that means that it is going to be in the positive direction because we are in the positive in terms of the point that I put. And it's the same displacement from your equilibrium. So if my amplitude is here, I need to make sure that the amplitude that I pick the point at is the same. So if I'm in phase, then the other point will be this one right over here. If we look at a different one, say for instance, right over here, well, now I'm in the negative, so the other point that is going to be in phase with this pink point is in the negative direction because they must be going in the same direction. And if my amplitude is this much for this pink point, it must be the same for the one that is in phase with it. So it should be about right over here.